Today, we will introduce VRRP in detail. First, we need to understand the functions of VRRP and be familiar with its working principles. Then, we need to master basic VRRP configurations to better understand the VRRP networking model and common VRRP issues. First, let's look at the working principles of VRRP. What issues can be resolved by VRRP? Let's look at an example. This network has one access switch to which multiple PCs are connected. The PCs are on the same network segment, and the gateway address is 192.168.1.254, the IP address of the Ethernet access interface of the router. When the PCs access an external network, traffic is first sent to the gateway, the router, for the data forwarding and routing. The gateway plays a vital role in helping the PCs access an external network. If the gateway router fails and has no backup device, the entire network connected to the switch is disconnected. This kind of failure is called a single point of failure. That is, a failure on a single point affects the entire network. This is because no redundancy has been configured for the network to ensure reliability. We use VRRP to improve networking reliability. On this networking, the routers R1 and R2 are connected to the switch, and some additional devices are also connected to the switch. They all belong to the same broadcast domain. The interfaces of R1 and R2 that are connected to the switch are assigned the IP addresses 192.168.1.253 and 192.168.1.252, which are the actual interface IP addresses. When VRRP is run on the two interfaces, they exchange VRRP advertisement packets. The exchange results are as follows. First, they generate a virtual router. See the figure. The virtual IP address of the virtual router is 192.168.1.254 and is not independently occupied by any router. The virtual router is configured as a gateway. Next, VRRP is used to elect a router from the routers to play the virtual router role. If R1 is elected to play the virtual router role, data packets are sent to R1. R2 takes over only if R1 fails. This smooth switchover process is completely invisible for PCs connected to a gateway. When the network is normal, a PC always sends traffic to a gateway. The elected router plays the master role and forwards traffic as the virtual router. When sending traffic to a gateway, a PC initiates an ARP request for the MAC address corresponding to the IP address 192.168.1.254. Both R1 and R2 receive the ARP request, but only R1, which is playing the master role, responds to the request. Traffic is then forwarded to R1 through the switch. R1 continues to route traffic and R2 discards data packets. If R1 or the link connected to it fails, VRRP detects the fault. VRRP then smoothly switches traffic to R2. The PC is completely unaware of the fault in switchover, and no manual changes are required. In summary, VRRP meets requirements for network redundancy. After VRRP is used, routers in the same LAN work together. However, you must ensure that the interfaces running VRRP are in the same broadcast domain. VRRP advertisement packets are based on multicast. In the same VRRP backup group, multiple routers' interfaces share one virtual IP address as the default address of a gateway in the LAN. The interfaces work together, but only one master interface among them forwards traffic. VRRP determines the master router. A backup router listens to the status of the master router. If the master router fails, the backup router takes over. Next, let's look at some VRRP-related terms. VRRP is implemented based on interfaces. A VRRP router interface can be added to multiple VRRP backup groups and serve different roles. A VRRP backup group contains multiple VRRP interfaces, which use the same VRID. However, a VRRP backup group can only have one master. A virtual router is a logical router abstracted for each VRRP backup group, and the router acts as a gateway. A virtual IP address is the IP address of a virtual router. A virtual MAC address consists of fixed bits plus the VRID. The master router forwards data packets in a VRRP backup group, and each group has only one master router. Other routers in the groups are backup routers. The master router keeps sending VRRP advertisement packets to all backup routers. If the master router fails, a backup router takes over. The virtual MAC address mentioned in the last slide is the MAC address of a virtual router and has a fixed format. The first 40 bits of a virtual MAC address are always 0000-5E0001, and the last 8 bits are the VRID. The master router has the following functions. 1. Responds to PC's ARP request packets. 2. Forwards IP packets sent to the virtual MAC address. 3. Periodically sends VRRP advertisement packets to notify a backup router of its status. A backup router keeps listening to VRRP advertisement packets from the master router. If the master router fails, the backup router takes over. A backup router does not respond to an ARP request carrying a virtual IP address and discards all packets sent to the virtual MAC address and virtual IP address. The VRRP state machine is simple, and only 3 states are defined. After going up, interfaces enter the initialized state and then send VRRP advertisement packets. These packets contain the interface priority and IP address for election. After both ends receive VRRP advertisement packets, they compare interface priorities. If the interface priorities are the same, they compare IP addresses. The router with a larger IP address is elected as the master router, and the other router enters the backup state. Once the election is complete, the router in the backup state does not send VRRP advertisement packets. The master router periodically sends VRRP advertisement packets to the backup router. Priorities may change when the network topology changes. In this case, the master and backup roles may change. If the network topology changes, VRRP detects the change and automatically decreases the priority of the master router so that a backup router plays the master role. Now let's look at the format of a VRRP advertisement packet. The packet contains the version field, the value is 2 for IPv4, and type field, the value is 1. Virtual RTR ID is the ID of a VRRP backup group. Count IP ADDRS is the number of virtual IP addresses configured for a VRRP backup group. The packet also contains the auth type and authentication data fields. The value of virtual RTR ID ranges from 1 to 255, and the value of priority ranges from 0 to 255. The value 0 indicates the interface is no longer used, and the value 255 is reserved for an IP address owner. VRRP defines 3 authentication types. The default interval between sending VRRP advertisement packets is 1 second. Now let's move on to the VRRP preemption feature. In this example, R1 functions as a VRRP router connected to the switch. VRRP is configured on GE 0/0/0 with a priority of 110. Before R2 is deployed, R1 unconditionally becomes the master router. After R2 is deployed, VRRP is also configured on R2's GE 0/0/0 and the priority is set to 120. R1 and R2 join the same VRRP backup group. In this case, can R2 preempt the master role of R1? The answer is yes, because the preemption feature is enabled by default in VRRP. After R2 is added to the VRRP backup group, R2 receives VRRP advertisement packets periodically sent by R1. These packets contain R1's priority. When R2 learns that its priority is higher than the priority of R1, R2 initiates VRRP preemption. R1 then does not send VRRP advertisement packets to R2, implementing a smooth VRRP switchover. Preemption can have a delay. The default delay is 0 seconds, indicating that R2 immediately sends a VRRP advertisement packet after finding that its priority is higher. If R2 is not required for immediate preemption, you can change the delay so that other protocols running on the router converge. Next, let's look at basic VRRP configuration. The figure shows the IP addresses of the GE 0/0/0 interfaces on R1 and R2. Here, the aim is to activate VRRP on the GE 0/0/0 interfaces of R1 and R2. R1 and R2 are added to the same VRRP backup group with a virtual IP address of 192.168.1.254. In normal situations, R1 is the master router. If R1 fails, R2 becomes the master router. First, configure R1 and R2. After completing basic configurations, configure VRRP on the GE 0/0/0 interfaces. The ID of VRRP backup group is 1. Associate the interfaces with the virtual IP address and specify priorities. Additionally, you can change the preemption delay. For configuration details, see the experiment example. After configuration is complete, you can run the display VRRP command to check detailed VRRP information. The command output shows that the VRID is 1. The status is master, the priority is 120, and the preemption delay is 20 seconds on R1. To check brief VRRP information, run the display VRRP brief command. You can also run the display VRRP command on R2 to check detailed VRRP information. The command output shows that the status is backup, the priority is 100, and the preemption delay is 0 seconds, indicating immediate preemption on R2. Let's look at another scenario. As we just mentioned, after R1 and R2 election is complete, R2 keeps listening to the status of R1. If R2 does not receive VRRP advertisement packets from R1 within a specified time, R2 determines that R1 is faulty and then changes to the master state. If both R1 and its VRRP-enabled interface are normal, but a VRRP-disabled interface on it fails, packets sent to R1 cannot be forwarded on. To resolve this issue, configure VRRP to track the status of the VRRP-disabled interface. If the interface goes down, VRRP decreases the priority of the master router so that another router plays the master role. In this experiment, R1 tracks the status of GE 0/0/1. The status of an interface is determined by both its protocol status and physical status. If the protocol status and physical status of an interface are both up, the interface is normal. If the status of GE 0/0/1 tracked by R1 is down, R1 automatically decreases its priority by a specified value, 30 in this example, so that another router plays the master role. For configuration details, see the example scenario, note the VRID, tracked interface, and value by which the priority is decreased. After configuration is complete, if the status of GE 0/0/1 tracked by R1 is down, R1 automatically decreases its priority by 30. Next, let's look at the association between VRRP and bidirectional forwarding detection, BFD. As we previously mentioned, R2 can change to the master state only when it does not receive VRRP advertisement packets from R1 within a specified time. VRRP advertisement packets are sent at an interval of 1 second. If R1 fails, R2 may take several seconds to detect the fault. To enable R2 to immediately detect the fault, associate VRRP with BFD. Configuration is very simple. Configure a BFD session on R1 and R2, and then associate VRRP with a BFD session. Next, on to the fourth scenario. First, let's look at the network in this scenario. R1 and R2 are connected to the same switch, and the switch is connected to two PCs. When the network is normal, R1 is the master and functions as a gateway. The internal network's all upstream traffic is transmitted to R1 for routing, and R2 has no traffic. In this case, network bandwidth and device resources are not fully utilized. To fully utilize bandwidth and link resources, configure multiple VRRP backup groups to implement load balancing. So how can we implement load balancing? Here, two VLANs, VLAN 10 and VLAN 20, are planned for internal network. The gateway addresses of the PCs in VLAN 10 and VLAN 20 are 192.168.1.254 and 192.168.2.254 respectively. First, configure VRRP backup groups on the interfaces of R1 and R2 connected to the switch. Then, associate VRRP backup groups 10 and 20 with VLAN 10 and VLAN 20 respectively. The interfaces also need to carry the two VLANs traffic. Therefore, we need to use sub-interfaces to meet this requirement. We create two sub-interfaces on each of the interfaces that correspond to VLAN 10 and VLAN 20 respectively, then configure VRRP backup groups 10 and 20 on R1's two sub-interfaces. Perform the same configuration on R2. To implement load balancing, that is, when the network is normal, VLAN 10's traffic is transmitted through the left link and VLAN 20's traffic is transmitted through the right link, perform the following configurations on R1 and R2. Configure R1 as the master in VRRP backup group 10 and as the backup in VRRP backup group 20. Configure R2 as the backup in VRRP backup group 10 and as the master in VRRP backup group 20. For details about R1 configuration, see the example scenario. For details about R2 configuration, see the example scenario. Let's look at the fifth scenario in which we configure VRRP on a Layer 3 switch. In this scenario, SW3 is an access switch and SW1 and SW2 are core switches. The network segment is 192.168.10.0/24. We need to configure a VRRP backup group on SW1 and SW2. Normally, SW1's VLANF 10 is in the master state. As we previously mentioned, VRRP is configured on a router's interface. For a Layer 3 switch, however, VRRP must be configured on a VLANF interface. First, we must configure SW1. The configuration is very simple. For details, see the example scenario. Note that the link type must be configured as trunk because the internal network has multiple VLANs. Perform related configuration on SW2. In the next scenario, we will take a look at typical VRRP and MSTP networking. Unlike the previous scenario, this scenario has a link added between the Layer 3 switches to form an inverted triangle Layer 2 switching network. A loop occurs after the link is added, and so a spanning tree protocol must be run. If the network has many instances, MSTP should generally be selected. This is a very typical way to lay out such a network. SW1 and SW2 are core switches, and SW3 is an access switch which is connected to PCs. The three switches form a triangle redundancy environment. Assume that the internal network has 4 VLANs: VLAN 10, VLAN 20, VLAN 30, and VLAN 40. When the network is normal, the upstream user traffic of VLAN 10 and VLAN 20 is transmitted over SW1, and the upstream user traffic of VLAN 30 and VLAN 40 is transmitted over SW2. If SW1 or SW2 fails, traffic can be automatically switched. We need to consider both VRRP and MSTP. From a Layer 3 perspective, SW1 is the VRRP master of VLAN 10 and VLAN 20, and SW2 is the VRRP master of VLAN 30 and VLAN 40. From a Layer 2 perspective, however, a loop exists. Therefore, we need to use MSTP to prevent loops. However, we cannot block interfaces randomly. We need to ensure that traffic from VLAN 10 and VLAN 20 is transmitted to SW1 over the left link and that traffic from VLAN 30 and VLAN 40 is transmitted to SW2 over the right link. For MSTP configuration, we need to map VLANs 10 and 20 and VLANs 30 and 40 to different MSTP instances. For example, map VLANs 10 and 20 to Instant 1 and map VLANs 30 and 40 to Instance 2. Then configure SW1 as the primary route of Instance 1 and the secondary route of Instance 2, and SW2 as the secondary route of Instance 1 and the primary route of Instance 2. In the spanning tree of Instance 1, SW3's GE0/0/23 is blocked. In the spanning tree of instance 2, SW3's GE0/0/22 is blocked. Now, we must configure SW3. On SW3, create VLANs and add the interface to the VLANs. Then configure MSTP. Map VLANs 10 and 20 to instance 1 and VLANs 30 and 40 to instance 2. On SW3, retain the default priority 32768 for MSTP instances 1 and 2. Next, related configurations on SW1 must be performed. Configure MSTP. Map VLANs 10 and 20 to instance 1 and VLANs 30 and 40 to instance 2. Then configure SW1 as the primary route of instance 1 and the secondary route of instance 2, and configure VLAN if 10, VLAN if 20, VLAN if 30, and VLAN if 40, and add them to VRRP backup groups 1, 2, 3, and 4, respectively. SW1 is the master of VRRP backup groups 1 and 2 and the backup of VRRP backup groups 3 and 4. Finally, perform related configurations on SW2. Next, let's look at some common VRRP issues. The first issue is a dual master fault for VRRP. In the fault, both devices are masters in the same VRRP backup group. The most common cause of this fault is that both devices are not in the same broadcast domain, so they cannot receive VRRP advertisement packets sent by the other. This is because VRRP advertisement packets are multicast packets. To enable a switch to support VRRP, you must ensure that multicast packets can pass through the switch. You can set a preemption delay to prevent this issue. The last issue is that a VRID conflict occurs within the same broadcast domain. As shown in the figure, VRRP is configured on the routers and switches, but the same VRID is set. VRRP uses VRIDs to distinguish between different VRRP backup groups. So if such a conflict as shown in the figure occurs, VRRP calculation is incorrect. The VRIDs in the same broadcast domain must be different. That's all about VRRP.